All right, it's started.
Wonderful. Hello, everyone, and everyone who's going to watch this after the recording. We're welcoming Dr. Apurva Gala to provide us an insight into the data science and analysis of this geothermal project. So please go ahead and start.
Thank you, Balnur. Hello, everyone. My name is Apurva Gala, and I have been involved with machine learning and AI for almost 8 years now. And I have a background in computer vision and a whole lot of time series predictive analytics and related problems, mostly in the subsurface domain. So let's get started. What I will, the way I have sort of outlined this particular presentation is that first we'll do like a quick overview of the entire problem statement, looking at the 3 parts individually, and then we can go through each part separately, and then for each part I'll try to sort of frame the background, the problem itself as a data problem, and then give you a few ideas of the kinds of algorithms that we can explore to solve that particular problem. I will say right off the bat, the most of the techniques that I will be discussing are not prescriptions. They are really providing you a data point of view at how to look at the data and what kind of problem solutions can you look for. So that's essentially what I will be doing. Not everything that I discuss has a direct relationship with what you should be using within the Datathon. So I wanted to set that stage before we begin, right? So please feel free to stop me at any time if you have any questions. Balnur, I might call on you from time to time to see if there are any questions in the chat, because I cannot look at the chat. And then please do help me keep up with the timing as well. All right. With that, if everything is if everyone's set, let's get going. Let's see how I can go to the next slide. All right. So I already talked about it. I'm going to go through the whole problem description to begin with, and then we can look at it in the bits and pieces and how we could solve each piece separately or together. So essentially what we have is, we have the larger problem that we are trying to solve is that we are trying to figure out where a geothermal production well should be located in relationship with an injection well that has gone through 3 stages of stimulation, and to support not just the stimulation data but also really understand how the stimulation has performed in the subsurface. What we have is, we have the seismic event data from 3 seismic monitoring wells that are also in the vicinity, right? So this is, again, where I'm pointing at is the tentative location of the production well. So this is really what we are after, this location. We have information about the location, not just the location, but also the injection well, what were the 3 stages of stimulation it has gone through. And then we have seismic event data from these 3 seismic monitoring wells that we will be using to sort of support our problem solving here. So are we on the same page here with just a larger context of what kind of data we have and what is the outcome that we're going after? Okay, so now let's go to sort of the details of the problem statement, right? So as I mentioned, there's one outcome that we are after at the end of the day, which is figuring out where is the location of the production well, or the optimal location of the production well. And the optimal is defined by the fact that we want to maximize the production of that from that well, right? The heat production from that well. Now, to facilitate the heat production, what has happened is the neighboring injection well has been stimulated. And as I mentioned, we have data from the 3 seismic monitoring wells. So when I say we have data from the seismic monitoring wells, what is it that we are actually looking at, right? So we have microseismic event data that follows each stage of the stimulation of the injection well, which is the 16A well. And how does this data manifest itself, right? So in terms of a 3D context, you can think of XYZ locations, points at XYZ locations in that 3D space. So you can visualize this data as a point cloud in 3D space, right? And now, given a bunch of cloud points in 3D space, the idea is to now find the best possible fit of 3D fracture planes or 3D planes that best illustrate that data, that point cloud data. Now we have 3 different simulation stages, which means that we have more or less 3 point clouds now that we can roughly think of the distribution of those points in the 3D space as this 3 point clouds. But again, this is a very simplistic explanation of the data. And so I will leave you up to you guys to really look at the data and figure out what is the best way to look at this data, or what is the best way to figure out a fitting problem over this data. But essentially, given these 3 point clouds, we are looking for 3D planes that fit these point clouds. And the manifestation of that, or what we get out of that, is the fracture plane interpretation that cannot just, it doesn't have to include a fixed number of fracture planes, but it can have many or as many fracture planes as the team deems necessary, which means whichever criteria is that the team is using as the best fit criteria to fit the 3D planes, it's up to the team to make that determination. Now, a bonus part of this problem statement is also that we are not only looking for a single interpretation, but we're looking for multiple interpretation or multiple realizations of the fracture planes. In order to determine the feasibility of the fracture realization, what is also provided to you is some contextual data. Now, this contextual data comes in the form of stress data from the Utah Ford site, where these wells exist and this data was generated. Right? So there are 2 ways to think about the contextual data and how you can incorporate that to revise your best fits. And we will come to that as I chop up the problem, then we go after each problem subset individually. So that's sort of the first part of the problem. So as the outcome of the first part of the problem, you will have at least a interpretation of multiple 3D planes in 3D space. Now, given the fact that you have an idea of these 3D planes and how they are spatially located with respect to each other, you should be able to construct a 3D map of these planes, right, relative to the location of the injection well. And now the goal is, obviously, you have this injection well data and you want to be able to figure out or the preferred location or the optimal location for the production well. So using the 3D map, you can augment that information with the 16A stimulation flow and pressure data to basically figure out what is the possibility for you to maximize the chance of hydraulic connections through these fracture networks between the 2 wells, between the injection well and the production well. And at the same time, you want to also be able to maximize or optimize the total surface area along these connections for to facilitate maximum heat transfer across the 2 wells. So this is sort of a 2-part explanation of the larger problem that we are posing here. So let me, before I go to the next slide, let me take a pause and see if you have any questions here. If there is any confusion around, what kind of data is available, what kind of outcomes are expected for each of these 2 parts. Panu, let me request you to look at the chat if there are questions there.
Right. So no questions in the chat.
All right. Okay. So in that case, let's move on to the next one. So the next slide is essentially a continuation of the problem statement, but what you have here are stretch goals, right? What we are hoping to come out of, hoping that your process of coming up with solutions for the 2 previous parts of the problem. Can you provide any suggestions to improve the design for future stimulations? Because the stimulations is a mechanism by which you are now enhancing the fracture network. So given that this is the fracture network, or these are the interpretations that you have been able to come up with, and based on that you have said, hey, these are the most optimal locations of the production well, can you also go one step further and provide suggestions of how to improve future stimulations that could enhance this existing fracture network that that you have been able to predict in many ways?
Dr. Apurva?
Yeah.
We have a quick question in the chat. The question is the location of the production well predefined?
No. So the location of the production well is the outcome, right? That is what we are expecting you guys to come up with, right? And the criteria for the location of the well is two-step. One is you want to be able to maximize the hydraulic connections between the production well and injection well, at the same time maximizing the surface area in the fracture networks or across those connections. So that is something we are not prescribing. That is really what we are after here. Does that answer the question?
Yes, thank you.
Okay. All right. So coming back to the stretch goals, I already described the first stretch goal. The second sort of stretch goal or is really, what are the key lessons that you learned while going through the process, while understanding the data, while understanding how to best fit the data, what criteria worked for you, what criteria didn't, and all of the lessons learned, even if those are simply lessons, or you did not probably come up with the best solution, that's fine. But how did that help you go to the next step or figure out what is the next step in your solution process, right? Those insights, those lessons learned are also something that has potential added value to this process, right, going forward. And it is along the same vein of improving the design for future stimulations, but how can we actually use the lessons learned to also not just improve future processes, but at least inform maybe the data acquisition or other processes that can help going forward as well. So a summary of the key lessons learned would be extremely insightful if you can provide it. And the final stretch goal would be to use some sort of predictive modeling approach to improve the interpretations of the fracture plane, all the well placement, right, with respect to sort of three criteria, right? One is something that optimizes the thermal breakthrough, something that keeping in mind the recovery efficiency and the stimulation efficiency. So these three would form basically additional criteria or optimization criteria on top of the interpretations and the well placement. And keeping these three criteria in mind, can you come up with predictive models to improve the interpretations? So that is sort of third part of the stretch goal. Now, I do not have it on this slide, but in the detailed document on the problem statement that will be made available to you, there are a few resources in there, predictive models and libraries people have put together, including Luke, who I don't know if he's joined the call or not, but he's part of the committee as well. One of his libraries is also one of the resources. So do take a look at those resources as well when you're looking at the predictive modeling part of the problem statement. Okay, so before I move on, again, the same question. Are there any questions? Because now I have kind of summarized the problem statement end to end, and now then what I intend to do is go into each part a little bit deeper and go probably a bit into the solution mode.
We have one question from Daisy. The question is, are there any suggested ways to estimate the conductivity of each hydraulic fracture plane?
Suggested ways to estimate the conductivity. So what I have in the next part of the presentation, right, are a few suggested algorithms that can help you come to that solution. But with respect to the specifics of that question, I would like to request help from Luke or maybe if Andy is on the call, or Kevin, if they can chip in.
This is Luke. Do you want me to chip in now or later?
Now, Luke, that would be great.
Sure. So first off, this is a really good question. There's a lot behind what you're asking there that's not easy to answer. A lot of times when people are modeling flow through fracture systems, they'll simply assume an aperture for the fractures and base their calculations off of that. It's typically hydraulic fractures are going to have an aperture of less than 2 millimeters. So that's kind of an upper ceiling for what you would want to consider for these kinds of things. The floor would be 0. What value you have between those values is pretty much an open question right now. But there is a little bit of literature out there that can help with estimating that. But you could also just kind of assume some distribution if you like, or a uniform value. Just kind of do the best you can, because there isn't really a true answer to that question. Does that make sense?
Seems like it does. So thank you, Luke.
Okay.
All right. Thank you, Luke. All right. In that case, let me move on to the next part. Oops, I went too far. All right. So now here is, I call it problem framing. So let's see if that's a, sorry, give me a second. Let's see if we can go about doing this, right? So this is something we already have kind of covered. This is the first part of the problem, which is given the data from 3 seismic monitoring wells, the seismic stimulation, the seismic event data. Can you use that in order to come up with fracture plane interpretations? This slide provides you a link to the actual seismic data on the Utah Forge website that you can go ahead and download. It also mentions ParaView here. So ParaView is a 3D visualization software that actually allows you to create, essentially inject the points and get a spatial 3-dimensional view of your seismic events. So if you go onto the website, and also the detailed problem statement also has a link to a really good ParaView tutorial. So that should help you get started in terms of doing the exploratory data analysis on this data. The seismic event data is basically encapsulated as a part of 3 CSV files. And yeah, I also quickly had talked about the additional goal. Now the additional goal is, given stress data, how can you now go ahead and define your fracture plane interpretations? So that's the stretch goal. Again, the stress data link for that will support this goal can be found in the detailed problem statement as well. So with that, let me just give you a snapshot of how one of these CSV files looks like. You have a lot of information upfront about what each of the columns mean. You can see that there is this XY depth information here. This is really what you will be able to map into ParaView to get sort of the spatial distribution of the seismic events. And depending upon which of these attributes of the data that you wrap around that location, you can change the location of those points in terms of their size, in terms of color, to get sort of a more descriptive visualization of the seismic event data. Which brings me to this slide. So the best of my knowledge, these images are created in ParaView. But what I really wanted everyone to focus on this slide is the image on the left here. This is kind of the description I was talking about when I began talking about the seismic event data, and where I described them as point clouds. So if you look within each of these ellipsoids, right, the idea is within each ellipsoid is the point cloud that is created by stage 1, let's say, of the stimulation of the injection well, stage 2 and stage 3 and so on. Now, these stimulations are carried out in a particular way, with different types of stimulation as well, in order to facilitate or generate these fracture networks, right? So given this kind of a 3D point cloud data, what are the techniques that can help you go from just point clouds to actually fitting different realizations of 3D planes within this point cloud space, right? And that is really something I'll discuss in the next slide, is what are the kinds of algorithms you can actually explore to do this. So let me go to the next slide and then I'll open it up for questions. So one of the ways to that you can really do this very effectively is you have the point cloud image that I actually showed, right? And within the literature of machine learning, there is this branch of machine learning which is called unsupervised learning. And unsupervised learning, or another nomenclature for it, is clustering, is really a set of techniques that allows you to partition the data depending on specific features. So one of the ways to partition the data that we were just looking at is to say, I want all of the points that are close to each other to belong to the same group. Or another way would be, I want all of the points across those all three point clouds, everything that has a similar temperature, I want it to be grouped in one cluster or one group. So clustering mechanisms are basically a way for you to partition the data based on or conditional on a particular feature of the data or a set of features of the data, right? So, but it is really giving you a clustering or a partitioning of your data objects, where the idea is the objects within a particular group are similar in one sense or the other. How they are similar or what you base the similarity on comes from the feature space. So is it the location? Is it temperature? Is it some other feature of the data? Or you might actually want to pose it as a multi-feature problem. So you want to say, if my points are close to each other, as well as also have the temperature within this particular range, based on those two features, now give me groups of these objects. So this is really the concept behind clustering. And I see there are a couple of questions in chat. Before I jump into the types of clustering, should we take the chat questions first?
Right. So that was mainly a comment letting us know that in addition to what you brought up, there is also tracer data. And tracer test is essentially injection of a tracer chemical into the hydraulic fracture and monitoring its movement. So analyzing of such data, the conductivity of each fracture plane can also be estimated. So the participants are welcome to investigate and look into that data as well.
Okay, great. Thank you. Thanks for that comment as well. All right, so with that, let me now talk about the types of clustering methods that we can use. Now, clustering has been around for a long time, and really, if you think about the ways in which the techniques have evolved, they are from fairly feature-based to extremely or really figuring out which features to cluster on. So there's a wide variety or wide range of algorithms to consider here, but I'll be basically talking about two types. One is called k-means, and the other is a density-based clustering algorithm. And the reason I've chosen to talk about these two are, I think, at least conceptually, they fit the problem space pretty well. Here I have also outlined a few resources on this slide in terms of the Python libraries that you can use, not just to ingest the kind of CSV data that is available on this on the Forge website, or something that I just showcased in the slide a couple of slides before. So Pandas is a really, really handy library to be able to do that. Very easy to learn. So yeah, it's along with that, it's not just about handling the data or extracting data from the CSV files and using it efficiently. There are a lot of Python libraries like scikit-learn and visualization libraries, again like Seaborn, that allow you to ingest the data from the Panda data structures directly into those libraries. So the resources that I've outlined here really work well with each other as well. So do take a look if you might find it useful. So with that, I'll start with k-means clustering. So in k-means clustering, there are two types of conditions that become extremely important, right? You want to be able to create, or k-means cluster goes after or allows you to create clusters that are very tightly connected with each other. So the sizes of the clusters are supposed to be as tight as they possibly can, right? So this is the parameter that you are optimizing when you are doing k-means clustering, is a very tight coupling within each cluster. And it is an iterative algorithm. So what it basically happens is you start off in your data space. So if you look at the animation on the right, you can see the crosses within each of the data clusters, and what the crosses really are is the centroid of each cluster. And it is basically showing you over iterations how that centroid moves in the feature space. So what k-means clustering really is good for is that it will allow you to optimize the sum of squared errors within every cluster. Right now, the one thing to keep in mind with k-means clustering is obviously you can cluster on one feature, let's say location, but you can also cluster on other features of the data. Right? So it can be easily extended to multidimensional feature-based clustering. One thing to keep in mind whenever you think about k-means clustering is you have to give it or specify a fixed number of clusters before you are actually allowing the algorithm to run with it, right? So what I mean by that is this k here, the k comes from the total number of clusters that you are asking the algorithm to come up with. So that is something that is a specification that you have to provide to the algorithm as a parameter, input parameter, right? So keep that in mind. The other thing to also note about k-means clustering is, since it is only heavily based on some optimization of the sum of squared errors, it is also extremely sensitive to outliers in the data. So always keep that aspect in mind. And whenever you think about clustering, right, even if you're not considering k-means, always have your eye or think about the outliers in your data. There are so one of the pitfalls in general of clustering is that it is very heavily driven by the criteria for clustering, right? By that, what I mean is, what are you basing forming the groups on? And if the criteria does not have enough constraints in it to figure out what are the outliers in the data points, your clustering algorithm is always going to be susceptible to that. So just that's a general comment about clustering. There are some clustering algorithms which are much better in terms of detecting the outliers and then making better fits of the data. But in general, and especially in the context of this problem that we are attempting to solve here, do keep the outlier point, the outlier or outlier detection as one of your criteria for coming up with better interpretations or better fits of the 3D planes. Any questions on k-means before I go ahead? All right. So the other clustering type of or class of clustering algorithms I'll be talking about is density-based clustering, which is basically less driven by the similarity of a particular feature of one data point to its neighboring data point, but it is more geared towards sort of this density as an optimization parameter, a kind of problem setting, right? So you will end up with clusters wherever there are high density of data points separated by low density regions. So one of just thinking about that, the way the problem is formulated, right, or this solution space is formulated for density based clustering, it gives you, so density or how close points are to each other is an automatic or implied way of saying what an outlier might be in the data. So keep that in mind when you're thinking about density based clustering, right? It gives you a natural sort of outlier detection mechanism in it. And typically when you compare something like density based clustering, which is, I think dbScan is one that is extremely famous. There is now a newer algorithm called HDBScan. It is very, very resistant to outliers as well. And this kind of clustering mechanism is extremely useful when it comes to the clusters that are not naturally spherical, right? So then they better maintain the shape as long as the density is an indicator of the shape of that of a cluster. Density based clustering methods do a really good job capturing that aspect of the data. So
Dr. Apurva?
Yeah.
We have a question. Apologies for mispronouncing the names. Francis is asking, which parameters are we looking to cluster?
Okay, good question, right? So again, you can, what you would be clustering on would be your seismic event data, right? Now, which parameters within that seismic event data that you would want to cluster, that is the space where your creativity is going to kick in, right? That is really, it depends on how you're thinking about the problem, the context of the problem, and really that will also bring you to different realizations of your 3D plane. So keep that in mind as well. So that is an open question. That's a question that we want you to really reflect on when you are coming up with the solutions. That being said, let me call on Luke for some guidance here as well, if he can provide some from the domain specific point of view.
So can you hear me okay?
Yeah.
So, there's, I guess the most obvious one to me is the clustering of the events together based on spatial location, proximity, as well as the timing of the events, to make sure that the microseismic events belong to either the same fracture or the same system of fractures. So that element of the clustering is hopefully relatively straightforward. It's basically time and space. But there's also other tricks that could be thrown at this that I'm less familiar with. Does that help at all?
I think that makes a lot of sense to me.
Yeah, no more questions on that, so I suppose it makes sense.
All right.
Thank you.
Okay, thank you. Okay, so if there are no more questions, I'm going to move on from density-based clustering. One thing I will say is we have only talked about the clustering part, right? So actually fitting the 3D plane on top of your clusters is a part that I haven't really addressed directly, but that, think of that as an obvious outcome of post clustering, right? So the clusters can actually help you figure out which points you want to use to do a better fit of your fracture planes on. All right. So yeah, so I think a lot of these pieces I've already discussed when it comes to clustering or in general unsupervised learning. You have to be able to be very, very careful when it comes to outlier detections. How do you define outliers in your data is really key here. And depending upon what clustering algorithm you use, the outliers might be detected for you. Obviously, multidimensionality of the feature, right? So one of the things that Luke talked about is the space and the time. So you can think of those two as two different features of the data on which you would do clustering. You can add features onto that. So it is the similarity can be multidimensional as well. Now,
Dr.
Yeah.
Apurva, we have another question from Jeff Bailey. The question is there any documentation on the event analysis method and specifically how the error term is calculated?
So this is again, I think, a question probably for Luke or Andy. I'm not familiar with the specifics of that data, domain specific consideration of the data.
Yeah, I also don't have the best answer for this, but there was some detail provided on this question in a previous session for the workshop that was held by Alita Vanilla. So
Okay.
you might be able to find some useful resources there to help answer your question. And in general, you know, there are a lot of different ways people characterize error for acoustic emissions. One that can be quite helpful would be the spatial error, you know, the X, Y, Z location uncertainty. But there's also amplitude uncertainty and a bunch of other terms that can be considered. So the database for microseismic events should have some error terms in there, if I'm not mistaken. And then some of them might be more qualitative, like a 0 to 1 scaled of error characterization.
Does that make sense? Can Jeff ask a question?
Right. So
Well,
Jeff,
typically there's a column called error, and it says the maximum error in the event location is consistent with the travel time pick and hodogram angle misfits. This can vary a lot due to the limited hodogram accuracy used to locate events in this stage, and units are in feet.
So is that a question, or are you basically, is it a comment describing the data?
I guess I'm wondering, like, is there documentation somewhere of, like, this is how we analyze the events from these 3 different wells? This is a sample event. This is what contributed to the location that we calculated for this event. And this is what contributes to the error estimate for this event.
So I think the best source or place to find if there is the contextual information that you're looking for would be the UtaForge website. I would also encourage you to sort of use the Slack channel to get in touch with Andy Adams. He's also one person who knows the data quite well.
I mean, for some of them, it may be mainly in depth. It may be, you know, easting and northing. You know, it may vary by event as well. To just assume that it's a spherical, like 219 feet, you know, may or may not be the right answer.
You are correct there, right? So I think what I encourage you to do is seek more clarification of the data. I'm probably not the best person to answer that question.
All right, thank you.
May I chip in a little bit from subsurface uncertainty point of view? The error bar is always there, especially with the sparse of the data. So one way is assuming the possibly maximum error bar we could have, what's the risk tolerance we could have, well, and some backup plan or mitigation plan. And that's what I typically do to handle the subsurface uncertainties.
Yeah. I guess all the receivers are quite a bit above the location of the events. So I'm wondering if maybe it's primarily a depth error. That's kind of, I'm just trying to figure out how to use the error term. Thank you.
Yeah, and then that's why I think in addition to the microseismic data, they also have tracer data. And different data sites point to similar error bar that typically give me some confidence.
All right, thank you.
Thanks, Mesong, for the clarification. Okay, so in the interest of time, the final thing I'll say here is I have provided some links to basic clustering algorithms, as well as I would encourage you to look at Jason Brownlee's clustering blog. It's a very, very nice description of clustering overall. Also at this stage, one comment I'll leave you with is do look at deep learning as a feature extractor. So models like autoencoders or contrastive learning, something you might be able to really leverage here, given that the space or the feature set on which you probably will end up clustering is really coming directly from the data. So perhaps an autoencoder type of embedding of taking those features and putting them either in a higher dimensional or specific to autoencoder in a lower dimensional space where you can actually better fit or come up with better realizations of the fracture planes might be a possible avenue for you to consider as well. So with that, I don't see any more questions in the chat, so I'm going to go ahead to the second part of the question of the problem statement. And the second part really builds on the first, which is now that you have been able to construct a 3D map or have a good contextual information about how the 3D maps or the 3D fracture planes are located with respect to each other, you can use information now about the stimulation flow and pressure data, the link to which is provided on this slide, and use this information to then figure out what might be the optimal location for the production well that will optimize maximizing the chance of hydraulic connections between the two wells. There are some criteria in the sense that the nominal separation distance between the two wells should be between 50 to 150 meters. So keeping those constraints in mind, using these two pieces of information, the outcome of the problem statement 1 and the stimulation flow and pressure data should be able to give you enough information to now figure out what is the optimal location of the production well. And now what kind of solution algorithms can we look at, and really the focus of the next couple of slides is really to go after what is the what are the mechanisms of maximizing connections between well locations is what the next set of slides really talks about in terms of the algorithms that you might look at. Oh, this is a, before I go there, this is a quick snapshot of how the stimulation data looks like. So what you basically have, I think there are 3 CSV files, again, stage 1, stage 2, and stage 3 of stimulation. And then every file also has a very comprehensive graph in terms of how the treating pressure changes over time or over the period of stimulation. And information like this is basically going to help you now, in fact, in many ways, refine sort of the orientations of those interpreted planes as well. All right, so now in terms of formulating this problem in a way that we can look at different solution spaces here, is that we want to say have the optimal connectivity between 3D planes that in the 3D space, right? So we can pose it that way. And one of the ways to look at these planes or the subset of of planes that the smaller fracture planes might belong to, the family of fracture planes, as Luke put it, we can imagine those to be sort of a graph or form of a 3D spatial graph, and you can think of each plane as a node in the graph. So if you look at the image on the right side here, essentially each of these nodes could be a fracture plane, and the connections between any two fracture planes is essentially, you can think about it as the intersection between the planes that could probably maximize the surface area of the combined the fracture intersection. So how you are going to make the connectivity between the planes, with whether and not just about the connectivity, but how much is the weight of each plane connecting to every other plane, is something that could possibly be a weight on this connecting edge between those two planes, right? So again, what I'm trying to say here is this is one way of formulating that problem into a solution space, as if you are thinking of the fracture planes as if it's a graph, and then you're trying to figure out, okay, what would be the shortest path from one plane in the graph to any other plane in the graph, right? And then possibly one plane in the graph is probably the one that might be intersecting with the production well. So that is one way of posing this problem. Now, in graph theory, the shortest path problem is really the solution that allows you to find the path between any two vertices of the graph, right? Such that the sum of the weights constituted by the graph is minimized. So this is what I was saying in terms of what is the weight that you are assigning the edge to this edge between any two fracture planes. That is going to be important. And what informs your weights is now the augmented information in terms of the stimulation, pressure, and flow data. You can think of that, incorporating that as a part of the weight of the edge between the planes as well. So there are many ways in which you can formulate this as a graph problem, and either you can look at it by as a solving the shortest path problem, or there are other more probabilistic ways you can go around about this as well. Again, this is one way to formulate it. This is not the only way to formulate it. So do keep that in mind as we go through the next few slides. So if we are now going to say, hey, I'm going to pose this as a graph problem. One way, let's first talk about the graph basics, right? How would you conceptually think of a graph? So graph would be a set of vertices, which is a set of vertices, the A, B, C, Ds, and you can think of these as your fracture planes or set of fracture planes. And then you have the connecting edges that basically connect any two fracture planes to each other, and then which of the nodes of the graph are connected by edges becomes or informs your adjacency list. So these are sort of descriptors of a graph, and then you should be able to map the different parameters of your data problem to different either the graphs, the edges of the graph, or the nodes of the graph, or the weights on the edges, or the adjacency list. So all of this is something you can use to define your graph upfront. Now, there are different types of graphs as well, which means it could be a directed or cyclic graph, which means there is a directionality between the connections between any two nodes. I have an image on the next slide, so I can talk a little bit more about that. It can also be a cyclic graph. It's an undirected graph, which is what you see here, which is basically the flow can be from A to B or B to A. There is no directionality in the flow. Again, whether you decided to go with a directed acyclic graph or just an undirected acyclic graph, that depends on how you choose to pose the problem. But if you do choose to go this route, the sort of the decision tree that you see on the right side kind of gives you a few solutions, or the ways to look at the different solutions depending upon what graph you have selected, right? I will be talking a little bit about one of these ways, but the assumption I'm making, or the way I'm posing this problem, is that this is a directed acyclic graph, and the weights of the edges are always going to be positive, right? So there is no backward flow. So that's hence the directed acyclic graph equivalency here. I see there are a couple of questions in the chat.
So it's mainly regarding where we can get the CSV files and etc.
Oh, you have the links for the data embedded in this PowerPoint, the kickoff meeting PowerPoint, as well as the document, the whole detailed document of the problem statement. And you are always welcome to go to the UtaForge wiki page, and it can essentially route you to many different or other data sources that are not for which the links are not provided within these slide decks or problem statements as well.
Thank you.
All right. So I'm going to talk about the shortest path algorithm that is mostly used for directed acyclic graphs, which is, as I said, is I think in my mind, one of a good way to pose this problem. And what this algorithm does is it gives you a way or to find in an iterative fashion the shortest path from any node that you select as your starting node to any node that you select as your destination node. Now, this particular algorithm, it allows you, so you can essentially find a shortest path from any source node to any destination node within your graph, right? But that is with a possibility space that you will have to play in when you think about what is the optimal connectivity between the two wells, right? So which nodes and that are your source and destination nodes, you can there's a possibility space in there as well. At the same time, you can also, so the way the shortest path is defined is that you are going to go through the minimum number of connections, right? Possibly this might be in contrast to the parameters that get you to maximum production, right, or maximum heat transfer along the path. So do keep that in mind. So the shortest path should also sort of align with your maximizing the hydraulic connection path in terms of heat transfer as well. So keep that that consideration in mind when you are going to pose this problem and figuring out what are the possibilities of your source nodes and what are the possibilities of your destination nodes. Again, like before, I have a few links to Python libraries to do this. NetworkX is an excellent graph library. It has everything that you might need to do a really simple representation of your data as a graph. Extremely powerful and very optimized data structures, graph data structures, I should say. A very comprehensive list of algorithms, an optimized list of algorithms to actually solve many more problems beyond the shortest path formulation for graphs as well. PyViz is a great Python library to visualize graphs, and it allows you to interactively visualize graphs, which is you can give it a series of inputs as to varying weights of the connectivity between the nodes of your graph, and it will basically go through all the realizations in real time. So it is extremely powerful in terms of giving you an idea of what the way you have posed the optimization problem, what the realizations will look like in the real time. So it's extremely useful. And GraphML is another Python library that actually allows you to learn the graphical model directly from the data. So if you want to go full-fledged machine learning route instead of doing any deterministic calculation, this is the way for you to go. All right, any questions here? Let me take a pause before I move on.
We have one question from Gerald Makaila. Hi, I'd like to ask the committee regarding the recording bootcamp sessions. Are there any links that can be accessed for the new participants? Yes, so we are sharing those through Slack. And if you're not on Slack, please feel free to reach out to me and other people on this team, and we will help you get connected on Slack. Other than that, we don't have any more questions, and we're almost at 1 hour. So we might go over a little.
Yeah, that's, I mean, what I will do it, I will leave it at that. I will just say, make one comment about this particular slide is a lot of the graph formulation we talked about was very deterministic graph formulation. The other way to look at it is from a probabilistic formulation, which is to basically say, I have an expectation or expected outcome, and I want to solve not a shortest path sort of optimization problem, but really an expectation maximization problem. And hidden Markov models is one very powerful way for you to do this. It allows you to define your data as if it was a series of time steps that go one after the other. So it allows you to do sort of this multiple probabilistic realizations of your connectivity paths. So there is, I have put the link to the hidden Markov model Python library, again, extremely handy library. It has a lot of inbuilt functionality. So this is one other probabilistic way of posing the graph optimization problem as well. I think this was really my final slide anyhow. So let me just say thank you to everyone for attending. I hope the session was useful to you. The recording as well as the slides will be made available to you through Slack. And if you have any other questions, always please feel free to reach out on Slack. And I see there might be a couple of comments or questions. Balno, could you help me with those?
Right. So far we don't have any questions. So please take advantage of this last couple minutes to ask final questions. If not, please reach out to us. All good? Okay.
All right.
Sounds good. Well, thank you, Dr. Apurva, very much for your time, for helping us digest the problems and sharing the tips on how to tackle those. And thank you, everyone who joined us today. Good luck on the Datathon.
Thanks,
Thank
everyone.
you.
Good luck. Thank you, Balno.
Thanks.
And thanks, Luke.
Thank you.